Alright guys, so the next unit is on chapter 14, which is dealing with the properties of gases. So, first and foremost, we have to recognize that gases follow the assumptions that the kinetic molecular theory told us previously. Alright, and we have elastic collisions, small hard spheres moving very fast and rapidly in random directions. So it's good to remember the kinetic molecular theory. All right, another property of gases is that they're compressible. All right, we can fit a large amount of gas or large volume of gas, we can compress it down and fill up a very small space. Two places where we might see this are in CO2 cartridges that you use for paintball and propane tanks. Now, what gases do, now there are some factors which affect pressure. Alright, and we said pressure is molecules bouncing off the surface of something. That's what's causing pressure. And there are three factors which affect pressure. The first one affecting pressure, especially when we have an amount of gas in a container, is the amount of gas. How much gas that we have. And if you have a lot of gas, it could be problems for those around you. We represent the amount of gas by the variable N. All right, N stands for moles. All right, so N is a measure of the amount of gas that we possibly will have. Another way that we measure gas is with volume. We can measure how much gas we have in terms of liters or milliliters. So with volume of gas, we measure this in liters, milliliters, one of our metric units of measuring volume. The last way we could have a factor which affects gas is by temperature, the temperature of gas. Now tomorrow in class, I'm going to do a little demo for you looking at how pressure is affected by both volume and temperature, or how pressure affects volume. So tomorrow we're going to be looking at these factors. But when we look at temperature of gas, we want to use a scale which helps us look at that temperature of gas, or a set scale. And the best scale to use, and the scale that we will only use when we look at gas, is Kelvin. Now, the way that we're going to get to Kelvin is we're going to take our degrees Celsius and add to that 273, and this will give us the amount of Kelvin that we have. Now, the gas laws that we have to worry about are four of them. The first one is Boyle's law. And Boyle's law, the variables with Boyle's law are volume and pressure. Now with Boyle's law, the assumptions are made that what's constant is the amount of gas and the temperature of the gas. And our formula for Boyle's law, and we're looking at the same gas under different conditions. And the Boyle's formula is pressure 1, volume 1 equals pressure 2, volume 2. And in terms of mathematical relationship, this is an indirect relationship. Because what this means is as pressure increases, volume decreases. And as pressure decreases, volume increases. So we have an indirect relationship between the two variables. The second law is Charles's law. And here our variables are volume and temperature. The amount of gas stays constant, as well as our pressure. Volume volume 1 over temperature 1 will equal volume 2 over temperature 2. This is an example of a direct relationship. What happens is as temperature increases, volume will increase, and as temperature decreases, volume will decrease. The third law is Gay-Lussac law. Our variables here are pressure and temperature. The amount of gas stays constant, and here our volume stays constant. And this relationship is pressure 1 over temperature 1 equals pressure 2 over temperature 2. As pressure increases, temperature increases, or vice versa. As we increase the temperature, we're increasing the pressure. Temp decreases, pressure decreases. Now, Charles's law and Gay-Lussac's law pretty much are self-explanatory. If we heat something, those gas molecules are going to move around more. And if they move around more, they're going to try to expand the sides of the container. If they're trying to expand and bouncing off the sides of the container more, there's going to be more pressure. This is also a direct relationship. Now, the combined gas law uses Boyle, Charles, and Gay-Lussac all in once. Our pressure, volume, and temperature are all our variables. The amount of gas stays constant. And we have a variable mathematical relationship. It all depends upon which way we look at it in terms of what's going to happen. Now, the formula is a combination of all the other formulas. So the combined gas law, P1 V1 divided by T1 equals P2 V2 divided by T2. So you should have this table down in your notes. Lastly, the thing I want you to look at is what's called standard temp and pressure, STP. Now, when I was growing up, STP stood for Stone Temple Pilots. Stone Temple Pilots was a Seattle-based grunge band. Pretty good music. But the STP for chemistry is not Stone Temple Pilots, it's standard temp and pressure. Standard temperature will always be 0 degrees Celsius. But since we're dealing with gases, we're going to look at Kelvin. Standard pressure is 1 atmosphere. Remember that 1 atmosphere is also equal to 760 millimeters of mercury, or 101.3 kPa. These numbers are considered constant, and thus they have infinite significant figures. Now, a little bit of algebra review. Combined gas law, P1 V1 over T1 equals P2 V2 over T2. If we want to solve for any variable, we first need to cross multiply, which would give us P1 V1 T2 equals P2 V2 T1. Then we will need to divide by the variables that we don't want to. Then we want to isolate our variable that we want to look at. So if this case, if we're looking for V2 or V1, we're going to divide here by P1, T2, which will cancel out, and divide here by P1, T2. So by solving, we'd have V1 equals to P2, V2, T1 divided by P1, T2. All right, these are the base notes. We'll discuss more of this tomorrow. We'll go over some demos for each of the types of conditions, and we'll start working on our math. Have a good night.